So now let's think still about volumes of revolution, but no longer the situation where the region we are looking at sits flush against the axis of rotation. So I have kind of a generic example here where we want to consider the region bounded between the curves f of x and g of x. And we want to think about rotating this around, we'll start with the x-axis, so rotating around a horizontal axis. And let's assume in this picture, to give it a little more specifics, let's assume that my x values range between a and b, and my y values range between c and d. So if I'm going to rotate this around the x-axis, then just like we saw with the disk method, because I have a horizontal axis, I think about my slices as being perpendicular to the axis of rotation. And I can see that those are going to cut into the x-axis. So I integrate with respect to x. So that matches up just like before. The difference here is that when you rotate this strip about the x-axis, notice that you're going to get a big hole. So in particular, if I'm looking at, can we see this kind of gap here. So when you rotate this around the x-axis, we're going to get what we like to call a washer, or something in a hole in the middle of it. Think about like a donut type shape. So in general, if I do that, and we think about, of course, we still have this delta x solid, in the disk method where you were against the axis of rotation, essentially if you looked at your slice from the side, it would be a circle. And if we do that here, we're going to get something like this, where the part of this that is solid would be everything in between here. Let me use that a different color just to avoid the yellow I used for the gap. So that part would come from this, and the empty hole in the middle comes from what I've highlighted in yellow here, that gap. So the only thing we have to consider is how do we find the volume of this kind of shape? So again, still keep in mind this is like looking at the side of it, the height would still be delta x. Well, to think of this, suppose that I have the radius of this inner circle is, let me make that visible. Let's call it R1. And the radius of the outer circle is R2. Notice that the area of what I have in green, you can think about it as the area of the larger circle minus the area of the smaller circle, which you can write as this. So pi times the outer radius squared minus the inner radius squared. And that gives me the area of that washer. And so if I wanted to find the volume, then I'm going to take that area of that face and multiply by my height delta x. So another way to picture this resulting three-dimensional object is it's as if you have a cylinder where you're cutting out a cylinder in the middle. So what we're trying to do is come up with a formula that's going to give the general volume of that. So that's just in general for the washer method. That has nothing to do with it specifically being rotated around a horizontal axis. But if I am rotating around a horizontal axis, then we're going to once again think about taking our interval of x values from a to b and dividing it up into n equal subintervals. So delta x would be b minus a over n. Then we can see that the v sub k, so the volume of just one of these pieces, now using my kind of side picture we have over here, we know that that's going to be pi times a difference of squared radius values times delta x. So this is that general structure up here. Again, I would put the delta x on the side. So in order to determine what goes in parentheses, I have to know what's playing the role of my outer radius and what's playing the role of my inner radius. So all that matters there is thinking about what's on the farthest edge away from my axis of rotation. So in this picture, f of x is further than g of x is away from the x-axis. So that's going to play the outer edge, or the outer radius. So in my picture, that would be like R2. So that means that I first take f of x evaluated at xk and square that radius, and I subtract the square of the inner radius. And the inner radius is now the distance from the x-axis to g of xk. And again, that's because g is closer to the axis of rotation. Didn't leave a ton of room here. So now we're at the point where we can see that my volume then would be approximately the sum of these washer volumes. Oops. And to get the exact volume, I'm going to take the limit as n goes to infinity of my approximation, and we're going to get here that v is then exactly equal to an integral against x. And we have pi because, again, we still have this kind of circular type object. However, what we have in parentheses is then f of x squared minus g of x squared. And it's important here that you notice we're squaring those individually. So it's not like we're squaring the difference. So if I then want to think about the bounds, just like we saw before, that means we have to know for our specific region, what are the values that x ranges over? And here we see that's from A to B. So I want to point out that in some sense, you could think of the disk method as like a special case of this, where the inner radius is just 0. So in that case, it'll reduce to what we had before. So one of the things that I hope we'll get practice with in my examples related to this is the importance, again, of kind of having a good picture and being able to think of how do I determine what is the outer radius and how do I determine what is the inner radius for different cases. Okay, so what about if we were instead to rotate around a vertical axis? I didn't redraw this picture. So for a vertical axis, we're going to think about, once again, just like we did with the disk method, slicing perpendicular to the y-axis. So again, we are going to think about integrating with respect to y when we are using this the vertical axis of rotation. So what I'm going to get, first of all, is yet again still this same kind of shape of a washer. So that's not going to change. One big difference is this dimension here is now delta y. So when I go through this process, I'm going to start by saying, yet again, delta y is the length of my interval. And notice my y values range from C to D in that picture. So my interval is not in terms of those x values. So again, just like we saw before, being careful to think about what y ranges over. And then my volume for one of my washers here is going to be pi times a difference of radius values squared times delta y. So just like we had to do when we talked about rotating a disk around a vertical axis, we need to think about our functions and express them in terms of y because we're integrating against y. So for this picture, the f function is still further away from the y-axis. So now I'm focusing on the fact that it is further to the right in some sense. But instead of writing f of x, I would want to put in what the inverse of that function is. So f inverse of y sub k, that's going to be my outer radius, so I square it. And by the same token, the inner radius would be the inverse g of y sub k, and I square that as well. So the same exact structure as the washer that we got for rotating around an x-axis, but of course, very importantly, kind of turning our view so that we're looking at the dependence on the variable y. So once I have that, my volume is roughly equal to a sum of the volume of the n different pieces that we have here. And that is an estimate. Once we have that, then I can take the number of pieces and send it to infinity. And so we end up with our formula for the washer here, where I get an integral of pi times my inverse of the outer function here squared minus the inverse of the inner function squared. We're integrating against dy, and my integral bounds are completely determined by the y values that specify the region at hand. So a lot of this looks very complicated with the notation, but hopefully in just a moment when we go through several different examples, we can see kind of the pattern of what we're looking at and how we're deciding about, is it with respect to x or y. So to do this, what I want to do is just think about one region, and then we're going to rotate it around actually 6 different axes of rotation, and think about just setting up the integral, but we're not going to go through the process of evaluating it because I do want to just stress the setup. So we're told that R is the region in the first quadrant bounded between the function y equals x squared and the function y equals x. So again, while it's not required, what I always would want to do is draw the associated region if I have to start thinking about rotating around any axes. And in fact, let me give myself enough room. So I'm going to take up a little bit more space here. So since we only have to set up, I can kind of use up a lot of this. So we're going to look at the function y equals x and the function y equals x squared in the first quadrant. And thinking about that, we're going to have y equals x look like this. And then y equals x squared is going to look something like this. So for this very first example, let me use a different color here. I'm going to rotate around the x-axis. The very first thing I notice is that the x-axis is a horizontal axis. So I know that my integrals will be with respect to x. So that's going to be one step. I also know that my general formula will involve a pi. And because there's a gap between my region and, so just to be clear, the region is between here. There's a gap between my region and the axis of rotation. I know that it's going to be a washer method. So now I need to think about, first of all, what's the outer radius? And so I look at my x-axis here, and I notice that the function that's further away from that axis is the function y equals x. So that's how I know that that's going to be the function that I square first. The closer function is y equals x squared. So that's playing the role of my inner radius. So we would end up really getting x squared minus x to the fourth. That's my integrand. And then of course I need to put in the bounds. Notice that this is the origin. So x starts at 0. And then to find the x value here, we have to think about where those two functions meet. So we're setting x equal to x squared. And that's the same thing as saying x squared minus x equals 0, or x times x minus 1 equals 0. And of course, one way those are equal is at 0, which we already knew. But another way is if x is equal to 1. So that's going to be the other place where they intersect. So that is the complete setup for the volume I would get by rotating that region about the x-axis. What if instead I rotate about the y-axis? So that's a vertical axis of rotation. The important thing then is I know right off the bat that I'm going to integrate against dy. We're going to have pi. And because there's a gap between the region and the y-axis, it's going to be a washer. So we have to think of a couple things. These functions are currently expressed as functions of y. However, I can quickly change that around. So if y is equal to x, we can write that as x is equal to y. And y is equal to x squared, we can say that x is equal to square root of y. Again, I only need to consider the positive portion because we're in the first quadrant. So now what we see, and that I wasn't able to emphasize in my general picture above, notice that which function is playing the role of the outer function actually swaps here. So now if I'm looking at the y-axis, the function y equals x squared is the one that's further away. So that means my outer radius is coming from that function, but I express it as square root of y. And then we're squaring it. My inner radius is coming from the function x equals y. And so that's what I square here. So it always matters. This is why I think it's really important to draw a picture so that I can really see the position of the function in relation to my axis of rotation. Now for the bounds on y, again, we know that this is the origin, so 0 for that. But we also know that up here, this point comes from x equals 1, and both y equals x and y equals x squared tell us that y would be 1 there. So not always the case that x values and y values are the same, but in this particular example, they are. So something that is a little different here, what if I instead rotate this, well, I didn't, to draw it to scale, it would be way down here, but what if I rotate it around something below the y-axis? So essentially y equals -1. So this is going to be very similar to the first question in that it's a horizontal axis of rotation. That means I integrate with respect to x. So my bounds are from 0 to x. I have a dx integral. I know that I have pi here. So all of this kind of carries over. Now, the difference is that we're changing our concept of what the radius would be in each case. I still have a gap between my axis of rotation and my region. So it's still going to be a washer method. So what we have to think about here, and sometimes a picture can help with this as well, if I were to look at, say, this x value, the outer radius would be this distance, and you can split that up into 2 pieces. So, running out of colors here, let's see. So this distance plus this distance. So that's the way I'm going to think about that outer radius. Well, the red line is exactly the y value. So if we're looking at the function y equals x, we're saying then that that's just going to be x. So when I'm at this point, the distance from the top line to that point is just x. And of course, the length of the blue line is just 1, because that's the line y equals -1. So to get from y equals 0 to y equals -1, we have a distance of 1. So I can say that that outer radius is in fact 1 plus x. So it's the same as the outer radius was in the first example, except I'm adding 1 to that distance. And that's exactly, so we square that because it's our radius, and that's exactly the same thing we're going to do to find the inner radius. The inner radius can be constructed by finding the y equals x squared plus that extra gap between the region and the axis of rotation, which is 1. So this would be 1 plus x squared squared. So left a huge gap between that and my dx. So now we can see how to adjust by kind of having still a horizontal axis of rotation, but one that's below our region that might have been shifted. If I instead look at the line x equals 1, so notice that in this case, here's x equals 1. That is a vertical axis of rotation. So we should be then immediately thinking that we're going to integrate with respect to y. So I have my y bounds, we have pi. It's going to be a washer because there's a gap between that region and our axis of rotation. And like I said, we're integrating with respect to y. And at this point, we've already done the work to rewrite our functions as functions of y, so we don't have to think about that. So now I want to consider how I'm going to find my inner and outer radius values. So it matters that my axis of rotation is now on the other side of the region. So if I were to pick a particular value of y, we could think about here, let me use pink here, and we want to find the outer radius. Notice that that is again coming from my linear function. So the outer radius is coming from the x equals y function, and the inner radius is coming from the x equals square root of y function. Now, how do we find that distance? Again, we can think about that in terms of pieces. So notice that we can find this distance, and subtract from that distance the distance from here to here. That would leave the pink distance. So again, just thinking about that picture. So if that's true, let's think about what those different quantities are. So the red line is just the constant value 1. It's always the distance between the y-axis and x equals 1. And we're subtracting from 1 the distance from the y-axis to the linear function. That function is the function x equals y. So we're going to put in that there. This is the outer radius when we're configured at the x equals 1 rotation axis. We subtract from that our inner radius, which is going to be the same process I just did, but with the x equals square root of y function. So I can think about taking the original distance of 1 and subtracting that distance of square root of y to get the leftover part there. And to be clear, that's going to give me this inner radius distance. And so I'm going to square that. So that would be the setup dealing with the line x equals 1. And again, what we're seeing here is kind of how we deal with an axis of rotation that is to the right of our region. So to continue this theme, imagine that we're going to rotate it about something above the region. And, whoops. In this case, that's y equals 4. So we just went through how to deal with rotating about a vertical axis that is to the right of our region. I'll point out that this is very similar to the idea of rotating about a horizontal axis that lies above our region. So now, if my axis of rotation is up here, notice that my outer radius is coming from the y equals x squared function. That's further away. And the inner radius is coming from the y equals x function. So right away, I can notice that this is a horizontal axis of rotation. I'm going to integrate with respect to x. And it's going to be a washer because there's a gap. So just like we did in the previous example, if I have to gauge that distance, I can take the entire distance, so 4, which is the distance between the x-axis and my axis of rotation, and subtract the distance between the x-axis and that y equals x squared function. So 4 minus x squared. That's going to be my outer radius. So that's the way to gauge the distance between this y equals 4 line up here and my curve y equals x squared up there. Then I can do the same thing for the inner radius. I'd start with 4 and subtract the y equals x function. Whoops. Lost my file. There it is. Subtract the y equals x function. And that gives me my inner radius, so I square that. So notice a connection here. If your axis of rotation is to the right of the region or above it, then we essentially see this idea of subtracting, thinking about kind of gauging a larger distance and then subtracting off something to get to that. Again, if ever in doubt, think about the picture and pick a representative x or a representative y value. And like I've done here with these lines, draw the red and the blue and the pink to kind of break this up into pieces. So we've also considered already in terms of horizontal axis, we've seen in number 3 how to deal with an axis that's beneath the region. That's going to be very similar to dealing with a vertical axis that's to the left, which is this last example we have here. So now we're saying, what if we were going to rotate about a vertical axis that's somewhere to the left of my region? Again, because it's vertical, I know I'm going to integrate with respect to y. And I'm going to get a washer because of the gap between my region and the axis of rotation. So much like we did in number 3, in order to rotate around this axis, which is further to the left of my region, I have to add to the radius that I got when I was just rotating around the y-axis. So here, we're going to think about the outer radius is coming from the curve function, which we're going to think of as x equals square root of y. But if I take x equals square root of y, that just gives me the distance from the y-axis to that edge. I need to add the constant value 2 to get the true radius. So I'm going to take 2 plus the square root of y to get that outer radius. And to get the inner radius, I'm going to do the same kind of thing to get 2 plus y, because we're looking at the linear function. And so that's showing us, again, in general, how we can deal with rotating about a vertical axis of rotation that lies to the left of our region. So we'll get some more practice with this. Again, you can notice the textbook problems do give you this kind of rote practice of setting this up. But the more you see of these, the more comfortable you should feel with deciding, is it a washer, is it a disc? Do I integrate with respect to x, with respect to y, and so on? And once you get a lot of practice with that, that should start to be a little bit more comfortable. And hopefully by seeing this one region rotated around several different things, this might help distinguish between some of the ideas.